Hello, I am your host today, and welcome to the Animated Scholar. Today, we're diving into the fundamental language of physics, vectors. They're the essential tool for describing pretty much everything, from the path of a planet all the way down to the force of a punch. So let's get right into it. Okay, imagine you're giving someone directions. If you just tell them, hey, drive 5 miles, that's not very helpful, is it? Is that 5 miles north, south, east? It's pretty useless. You need two key pieces of information, the distance and the direction. And this is the exact problem that vectors were designed to solve. So what is this powerful little tool that manages to wrap up both distance and direction into one neat package? Well, that's the vector. And it's pretty much how physics maps out our entire world. So let's break this down. The physical world can be split into two types of quantities. On one side, you've got scalars. These are just plain old numbers. Think of your mass, or the time, or the distance you ran. They only have a magnitude, or a size. But on the other side, we have vectors. And these are the cool ones, because they have both magnitude and direction. For instance, velocity isn't just 60 miles per hour. It's 60 miles per hour north. Force isn't just 10 newtons. It's 10 newtons downward. That little extra piece of information, the direction, is what makes them so incredibly powerful. So what does a vector actually look like? Well, graphically, it's just an arrow. Super simple, right? Its length tells you its magnitude. So a longer arrow could mean a stronger force or a faster speed. And of course, the direction the arrow points, well, that's the vector's direction. It's a really simple, elegant, and powerful idea. So an arrow pointing, say, northeast is useful, but in physics and engineering, we usually need to be a lot more precise. How much north is it going, and how much east? To figure that out, we have to break the vector down into its components. You see, any vector, like this one we're calling A, can be thought of as the sum of two simpler parts. We can break it down into a purely horizontal part, which we call AX, and a purely vertical one, AY. These are its rectangular components. It's kind of like taking a diagonal shortcut across a field. It's really just a combination of moving across and moving up. And figuring out the size of these components is actually pretty easy if you remember a little bit of high school trig. If you know the vector's total magnitude, A, and the angle it makes with the horizontal, which we call theta, you can find the horizontal part with cosine and the vertical part with sine. The key takeaway here is that any complex direction can be perfectly described with just two simple perpendicular numbers. Okay, so we know how to define vectors and how to break them down. But what happens when we want to combine them? The first method we're going to look at is called the dot product, and it's designed to answer a very, very specific question. And that question is, how much do two vectors actually line up with each other? Picture this. You're pushing a box across the floor. If you push it straight forward, all of your force is helping. But what if you're pushing downward at an angle? Well, then only part of your force is actually moving the box forward. The dot product is what helps us calculate exactly how much that effective part is. The dot product, which is sometimes called the scalar product, gives us a single number, a scalar, as the result. And this number tells us how much of vector A is aligned with the direction of vector B. If they point in the exact same direction, the result is big. But if they're perpendicular, at a 90-degree angle, the dot product is 0, because neither vector is contributing anything to the other's direction. And this isn't just some abstract math trick. No way. It is fundamental to physics. The concept of work, something we talk about all the time, is literally the dot product of force and displacement. And the same thing goes for calculating things like mechanical power or even the flow of an electric field. All right, so if the dot product tells us how much two vectors are aligned, our second method, the cross product, is all about what happens when they are not aligned. Now, here's the big difference. The cross product, or vector product, doesn't give you a number. It gives you a whole new vector. And the direction of this new vector is really special. It's perpendicular to both of the vectors you started with. It literally points into a completely new dimension relative to the first two. So, if you have two vectors lying flat on a table, their cross product is either going to point straight up or straight down. But which one is it? This has puzzled physics students forever. But don't worry, there's a simple trick to figure it out. The trick to solving this puzzle is the famous right-hand rule. It's a really simple physical way to find the direction of that new vector. Let's walk through how it works. Okay, grab your right hand and actually try this with me. First, point your fingers straight out in the direction of the first vector, A. Got it? Next, curl your fingers toward the direction of the second vector, B. Now, whichever way your thumb is pointing, that's it. That's the direction of the new cross product vector. It's a simple, foolproof way to get it right every single time.
So we've defined vectors, we've broken them down, and now we know how to multiply them in two completely different ways. But why? Why go through all this trouble? Why does any of this matter? Well, the cross product is basically the language of rotation. Torque, that twisting force that lets a wrench turn a bolt, is a cross product. The same goes for angular momentum, the thing that keeps the spinning top from falling over. By using vectors, we get the tools we need to precisely describe and predict anything that spins.
From the tiny interactions between subatomic particles to the huge sweeping orbits of entire galaxies, vectors give us the framework we need to understand it all. So this brings up a really interesting question. What else could this powerful language of direction and magnitude help us describe or predict in the future? Please give your opinion in the comments section. Do like the video and share it with your friends. Last but not least, subscribe to The Animated Scholar.